right, so I have this video embedded in the PowerPoint. I'm going to play, and it's going to go over logarithm.
How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the fourth is 10,000. So log base 10 of 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators. If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log
Hmm.
64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.00000000398 and 0.00000000398 quickly on a calculator. Punch negative log of each of those numbers, and you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
All right, so here we go. Again, the definition of log, as he says, base raised to what power equals a number. So examples here, 5 squared equals 25. So the log 5, 25 equals 2. All right, so there's some rules when dealing with logs. For instance, adding logs, you would multiply the numbers. Subtracting logs, divide the numbers, and then log with a to the nth power. This is how you would solve this. Like if you need to solve what n is in this, you would use log to get the exponent down from whatever number you have, and then log to n squared gives you this. So this, not something necessarily you'll remember off the bat, but definitely have it sort of like marked in the back of your book, know where to reference it, and refer to it when needed. Some examples for you guys to review. All right, now let's get into some trig. So we have in trig, there's sine, which is the opposite over the hypotenuse, cosine, which is the adjacent over the hypotenuse, and tangent, which is the opposite over the adjacent. Commonly known as SOHCAHTOA. So there's one thing you remember, let it be SOHCAHTOA. Actually, there's lots of things. SOHCAHTOA is definitely one of them. And by the end of this course, you will definitely remember SOHCAHTOA with all of the trig that we will be using with force vectors. So here, an example, sine opposite over hypotenuse. So opposite meaning opposite of the angle in question. So we have this angle, right? And then opposite of it, this is opposite of the angle, is the A, and then adjacent, right next to it is that, and then we have, of course, the hypotenuse. So just to get a little bit more clear. So cosine here, it's adjacent over hypotenuse. So the adjacent is 6. Hypotenuse is the 10. Be 6 over 10, and this reduces 3 over 5. Tangent, opposite over adjacent. Opposite over adjacent, 6. So 8 over 6 comes 4/3. All right. So this is useful if you want to find the measure of one side and you only have 2 other sides. You can use the Pythagorean theorem, which is a squared plus b squared equals c squared. A squared plus b squared equals c squared. So here we have a 3 plus 4 equals c squared. Now we have sine if we want to find this angle, okay? So we use the Pythagorean theorem to find this, the 5, and then now we want to find this angle. So it's going to be opposite 4 over the hypotenuse, which is 5, or you can use cosine, which is going to be the adjacent, which is 3, over the hypotenuse, 5. Now that we have being that we started off with just the adjacent and the opposite, we could have found the angle just with those numbers using the opposite over the adjacent, 4 over the 3. And you're gonna, again, this is also going to be something that will become second nature after no time at all. Let me get rid of this. Yeah. All right, so find the sine, cosine, the tangent of angle A. So given the fraction and decimal answer, rounds to the 4 decimal places. So sine A, opposite over hypotenuse. You have opposite over hypotenuse. After, of course, plugging this in the calculator, we get A. cosine, so on and so forth, using tangent. You guys got it. So this is gonna come in handy when doing all sorts of calculations. So here's an example: surveyor standing 50 feet from the base of a large tree. Surveyor measures the angle of elevation to the top of the tree as 71.5 degrees. And how tall is the tree? Drawing it out, and I always recommend sketching and drawing these problems out. We get this 50 feet, the angle, and then the question of, well, how tall is this tree? So what would you use here? You have the angle, then you have the adjacent, and you're looking for the opposite. So using SOHCAHTOA, which function are you going to use? There we go. Tangent, opposite over hypotenuse. Hmm. Okay. Wait. This doesn't look right to me. This isn't right. This is wrong. This is wrong. You don't have the hypotenuse. It's not the hypotenuse. I need to change this. Okay. Well, this is an example of sometimes things aren't right. Okay. So what we have here is the adjacent, not the hypotenuse. Sorry, I got these slides from somebody else. That is wrong. All right. We're going to use so so that should be an O and an A. All right. So this is opposite over adjacent. Yeah, sorry about that. I bet that confused their students. All right. Yeah, let me hammer this in a little bit more. This is not hypotenuse. This is adjacent. All right. There you go. I'm certain you will remember this now. Okay. Yes. I'll take this further. All right. There are other examples you can go over. All right. But I want to quickly get to something a little bit more interesting and intrigue, and that is the unit circle. So let's go through this video right here.
Hey, it's Professor Dave. Let's memorize the unit circle.
He knows a lot about all kinds of stuff. Professor Dave explains.
Math students often have trouble with this thing. It's called the unit circle, and it's just a circle with a radius of 1 superimposed on the coordinate plane with the center at the origin. Then we have all the angles that are multiples of pi over 6, as well as the multiples of pi over 4. And we have to know the sine and cosine values for these angles. Let's quickly go over some key points about the unit circle that will make it very easy to remember. First, we must recall what sine and cosine are. From SOHCAHTOA, sine means the length of the leg opposite the angle over the length of the hypotenuse, and cosine means the length of the leg adjacent to the angle over the length of the hypotenuse. For each angle on this unit circle, we are constructing a triangle by drawing a line from this point straight down to the x-axis. The hypotenuse of this triangle is the radius of the circle, which is always 1, and the two legs are each some value less than 1 depending on the angle. What we must understand is that every point on this unit circle has an x-coordinate equal to cosine theta and a y-coordinate equal to sine theta. Take 0 as an example. There's no triangle, but since the radius of the circle is 1, we know that the cosine of 0 must be 1 because the x-coordinate of this point is 1. Likewise, we know that the sine of 0 must be 0 because the y-coordinate of this point is 0. It will be just as easy to figure out the values for half pi, as this point has the coordinates 0, 1. So the cosine of half pi must be 0, while the sine of half pi must be 1. At pi, we get -1 and 0. And at 3/2 pi, we get 0 and -1. Once we make it to 2 pi, we are back where we started, and the cycle continues. Now, what's important to see is that the cosine and sine of any angle other than these must be somewhere in between -1 and 1. Let's take pi over 6, for example. In the last clip, we evaluated the trig functions for these two special triangles, so if you missed that, go check it out now. Otherwise, just take my word for it that the sine of pi over 6 radians, or 30 degrees, is 1/2, and the cosine is √3/2. That means that the coordinates of this point are √3/2, 1/2. For quarter pi, we have this other special triangle, and both the sine and cosine of 45 are √2/2. So these are the coordinates of this point. For 2 pi over 6, or pi over 3, we have the same values as for pi over 6, but reversed, since it's the same triangle, just looking at the other angle. That means that these are the coordinates of this point. And that wraps up the first quadrant. Now here's the thing that makes this so easy to remember. We see some fractions and some roots which may seem unrelated. Just for the sake of creating a pattern, let's replace 0 with √0/2, since √0 is 0. Let's change 1/2 into √1/2, since √1 is 1. Then we have √2/2, √3/2, and let's change 1 into √4/2, since √4 is 2, and 2/2 is 1. Now, if we look at the sine values for these angles, which correspond to the y-coordinates of the points, we can start at the x-axis, where the y value is √0/2. We climb up to √1/2, then √2/2, then √3/2, then √4/2. We could do the same thing with the x values, which correspond to cosine values for these angles, starting with the y-axis and then moving to the right in the positive direction. Again, we hit the same values. So all we have to do is remember this one numerical sequence and that the coordinates of each point take the form of cosine theta, sine theta, and we will never forget any of these values. Let's return these values to their simplified forms and then extend things into quadrant 2. We can see that sine values, or y-coordinates, will remain positive as these points are above the x-axis. 5/6 pi will have a sine of 1/2, just like 1/6 pi. 3/4 pi will have a sine of √2/2, just like quarter pi. 2/3 pi and 1/3 pi each have a sine of √3/2. Now for the cosine values, it's the same thing, except that they are now negative, as they are to the left of the y-axis. Going into the third quadrant, both sine and cosine become negative, as x and y are both negative, but it's still all the same numbers. And into the fourth quadrant, cosines return to being positive, while sines remain negative. Knowing this, we could take any of these angles and immediately know the sine and cosine simply by visualizing the unit circle. Take 4/3 pi, for example. To get the sine of this angle, we simply locate the angle, which can also be thought of as this reference angle, or 1/3 pi, but in quadrant 3. Then we recall that sine corresponds to the y-coordinate of this point, and we just move downwards until we get there. 0, -1/2, -√2/2, -√3/2. To get the cosine value, we just remember that cosine corresponds to the x-coordinate of the point. 0, -1/2. We aren't calculating anything. We just have to memorize the locations of the angles, this one numerical sequence, and what the coordinates of the points represent. Once this is ingrained in you, you'll never forget it, so just stare at this until it makes sense. When you have it, it becomes trivial to evaluate trig functions for any common angle. Take something like the tangent of 14 pi over 3. 12/3 pi is the same as 4 pi, and that's twice all the way around, so we can subtract that from the angle to get 2/3 pi. That gets us right here. Now tangent is sine over cosine, so let's take the y value of this point and divide by the x value of this point. And that gives us -√3. What about the cosecant of -17/4 pi? This time we are going in the negative direction. 16/4 pi is the same as 4 pi, so if we get rid of that, we are just left with -1/4 pi. That puts us here, where cosine is √2/2 and sine is -√2/2. Cosecant is 1 over sine, so we take 1 over -√2/2. We can therefore just flip this over to get -2/√2, and then we multiply by √2/√2 to get rid of the radical on the bottom. That leaves us with negative.
Let's just think back to where we began, right? We said this topic is called trigonometry, right? Which is
√2. It may take a little while to get accustomed to using the unit circle so quickly, but it's just a matter of practice. When you're ready, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right, so let's go and take this back here a little bit. Okay.
And then we multiply.
Oh, okay.
Hey, it's Professor 18 pi over 3.
Do, do, do.
To get -2/√2, and then we multiply by √2/√2 to get rid of the radical on the bottom. That leaves us with negative.
Okay, so that's one way to remember the unit circle. And yeah, I would recommend drawing this out a lot, like he says, practice, practice, practice. But let me pull up something else. I'm gonna use good old-fashioned paint. There we go. Paint. All right. So, and all right, let's say, all right, so first thing to think about is we have X and Y. Actually, I do this Y and then X, right? So then X, then Y. All right. So if we have sine and cosine. Let's think about this right here. One of these is, we can attribute one of these more to X and the other to Y, okay? So, and what do I mean by that? So let me take this, select all of this right here and bring it down, okay. Actually, let me just do this, okay. So let's say we have the unit circle. Yeah, I'll call that a circle. Okay. We have this right here. All right, where this is the, of course, as always, the, no, what was that? Okay, that's, anyway, this is the X. The X. And of course we have the Y in the vertical. Okay, so X is cosine and Y is sine. Here's how we can look at this. Okay. Let's see. Let me find his unit circle.
To using the unit.
Oh, okay. So his unit circle right here, we see at pi 1/2, 0, and there's a 1, okay? And then here, there's a 1 and there's a 0. So which one applies to which? Okay. Well, this is how we're going to figure this out. So let me pull this back up. Where'd my paint go? Okay. Let me actually just do this. Control C. All right, there's a whole bunch of ugliness going on. Don't
Circle
worry.
so quickly.
I will make this make a little
But
bit
it's
more
just a matter of
sense. Okay. Select all of this. Deleted. Control B. All right. Let me shrink this down a bit. All right. So if I take sine, if I take the unit circle, and if I draw out a circle like this one here, and then I, on top of the circle, put sine and cosine like this. Ooh. Like this. Okay. So what do I mean by this? First thing I'm going to do is move this over here. And oh yeah, I can just draw a circle like this. Cool. I think there's a little bit. Okay, that's good. Draw this circle. Beautiful. Okay. So draw a circle. Then I'm going to take this and I'm going to draw a line. Okay, can't be a perfectionist right now. Oh, so close. That's okay, whatever. Right. So then it's like, well, what's this? Is this sine or cosine? Well, let me just again. Let me say this will look better than me drawing out with my finger. Okay. This a little bit more visible. That did nothing. All right, but this bam. Sine, cosine here. All right. So this is what I mean when this is the trick. Draw the circle, you draw this, and you label sine and cosine. SIN kind of looks like this. COS kind of looks like this. All right, so this is a good starting point. So then you know which is which, okay? At least here, okay? Well, if you know what it is when it's labeled here, then you automatically know what it is here, because here it's just the opposite. See that? Okay. Then we can actually get a little bit more info from that. So the I hate to get this stuck in your heads. Okay, this is how this goes. X is cosine, y is sine. You can say that like this. X is cosine, y is sine, y is sine, y is sine. X is cosine, y is sine, y is sine, y is sine. X is cosine, y is sine around the unit circle. Yep. That's how I learned this. That's what they made us sing in class. So let's sing it all together. No, really sing it and mean it. X is cosine, y is sine, y is sine, y is sine. X is cosine, y is sine around the unit circle. One more time for the people in the back. X is cosine, y is sine, y is sine, y is sine. X is cosine, y is sine around the unit circle. I apologize for doing that to you. Okay, but you say that and you will remember it. Okay, so now that's stage one. X is cosine, y is sine. So what does that mean? Well, here cosine is x. Well, what is x at this point? It's 0. And at this point, the unit circle is only a unit 1 away, right? So then at this level on the y-axis is 1. So the sign is 1. All right. So now we have 2 parts of the unit circle down. All right. Now let's fill in some of these other blanks right here. We have some basic angles that we go with. We have 30 degrees. Here, let me do this. So we have 30 degrees. We have 45 degrees. And then we have 60 degrees. All right, so we have, and once you have all of these memorized, once you have this quadrant memorized, then the rest of it will come in. All right, because if this is the x-axis right here, all right, if this is all the x-axis right here, then we know that this part of the x-axis is positive. And then we know that this part of the x-axis is negative. Then we can see over here, all of the x's are negative. And we know that this right here is still positive. That just looks awful. We know that's still positive on the y-axis. So it makes sense that all of these, which are attributed to y, their sign, are still going to be positive. So let's figure out how we can memorize just what these angles are for each of them. Okay, so let's do this. There's a visualization trick that you can do, and that is this. Let's say, let me take this back some more. Right. Let's look at angle 60 right here. Okay. 60 degrees. Okay. So this is 60 degrees from here. Okay. What does that mean? Here's kind of what I like to do. I like to look at it like this. I'm just gonna Control X this so I can bring it back. Right. I have a piece of wood. It's kind of like a door, right? Okay. If I have a wall, and then if I have this, oh, that's nice. Okay. All right. So check this out. Let me actually. Okay. So if I open this door this far, and this far being 60 degrees, okay? Let's say this is 60 degrees. Now imagine using the power of imagination. Let's say that there is a large light right here. Okay, a large light, and this light is shining rays down. Okay. All right. All right. And this light's shining rays down. Okay. Then this door right here is going to cast a shadow. Right. All right. This door is going to cast a shadow. So how much of a shadow is this door going to cast? Well, we have these rays coming straight down, illuminating this black backdrop. Okay. And the shadow is going to be created by this door. It's going to be here. Right? This is all going to be shadow. And if we were to measure how much of the door is now in shadow, it is going to be half. Half of this backdrop is going to be in shadow. So this backdrop being the x-axis is now going to be, half of it is going to be in shadow. All right. Okay. Then if I delete this, then Control V, this guy back in. we know that when the angle is 60 degrees, the x right here, right here is going to be 1/2 down here, 1/2 of this x axis is going to be in shadow. So that means cosine 60, we're going to get 1/2. Okay. Now, conversely, if x is cosine, oh, dang. If x is cosine, y is sine, then we have 30 degrees right here. All right. Then this right here, oh, that's too much red. This right here is going to be half of the y-axis. Okay, so you can see this right here. Okay, so half of the y-axis. So looking at this like this, so we see these numbers, we see two numbers in each one of these parentheses. Okay, so look at that right there, two numbers in each set. So if we look at this like it is x comma y, now we can start to make sense of all this. Okay. So we got this. This is all you have to do. So now you can figure out where the 1 and the 0 is on the x right here, and where the 1 and the 0 is on the y, and you know where the 1/2 is for each of them. All right, and then you have all these other numbers. Now, all the other numbers might seem confusing, so let me make that not confusing. All right, let's do. Oh, okay, now let's do this. I'm gonna draw this out so it's super easy to remember. Get this right next to here. I'm gonna add some and now I'm gonna add text. All right, so I'm gonna draw this out with my finger. All right. I have all these angles here. This is 45 degrees. And then, oh. And this is going to be 30 degrees, okay? All right. Now, here's how I do this. All right. I'm going to remember 1, 2, 3, 3, 2, 1. All right, so let's do this right here. So I'm going to remember 1. Let me back this up a little bit. I want to remember 1. Sorry, wrong space. Okay. So this little trick I'm going to show you. So we know where it is, where it's 1 and where it's 2. And now this is just going to help us remembering what these 3 angles are. Okay. So I'm just gonna just applying just to these 3 angles. Let me sort of that right here, and then right here. Okay, so going to say, going down, and say 1, 2, 3. Right? 1, 2, 3. Perfect. That's easy to remember. Okay. Then I'm going to square all of these, or square root all of these. Okay, cool, cool. Now I'm going to divide them by 2. 2, 2, 2. Look at this guy. What's this? What's square root of 1? Well, it's just 1. So then this is really just 1. All right, there we have 1/2 root 2 over 2, square root of 3 over 2. So just remember 1, 2, 3, square root them, divide them by 2. And that's how you can remember these primary 3 angles in here, right? And then this is going to be for the for cosine, because you're starting here, and then you imagine that door, so that's going to be 1/2. So you already know that you're going to be starting with 1 right there. And then with the sine, everything's just going to be the opposite of that. So then if that's 1, 2, 3, then this is going, if it's 1, 2, 3, then you're going to go, you can go back up and say, well then 1, 2, 3, square root, square root, square root, divided by 2, divided by 2, divided by 2. And then you can just flip the sign as needed. And that's a really good way of how to remember the unit circle. All right, and there I think I'm going to take a little break on this part, let you guys practice.